Hi, it's time for another math easy solution. Time to discuss further into calculus with parametric curves and now look at areas. Just go over an introduction on it and how to find areas of parametric curves or underneath parametric curves. In my earlier videos I went over tangents and now we'll go look at areas. Quite interesting. So first let's recap. So on areas we know that the area under a curve y equals f of x from a to b, well that is just equal to a integral a to b, so we could write this as an integral. So integral of f of x dx, again from a to b, and this is if we're looking at an area, then we're just going to assume f of x is greater than or equal to 0 at all times, so that we're dealing with an area. And if we were to graph this out, so this is x, this is y, and let's say we had a positive f of x curve like that, y equals to f of x, so the integral represents the area underneath this curve like that. So that's what the integral represents. So a equals to area underneath, and that area is equal to this integral. Yes, so now if we were to write the curve, if the curve is given by parametric equations, x equals to f of t and y equals to g of t, and it's traversed once as t increases from alpha to beta, basically what it means is because these parametric equations, like I've shown before it, you can go back and forth unlimited times depending on whatever the t value is. We're going to assume that it only goes once. So in this case we'll assume that at this x equals to a, we have a t value inside that equals to alpha here, and then at x equals to b we have t is equal to, well, beta over there, and then the corresponding x and y coordinates are over here. And then we can adapt the earlier formula by using the substitution rule for definite integrals. So we can change this integral, and basically the idea is to substitute the x's, or basically substitute this, use the substitution rule to remove the x variable and instead deal with t. So to do that, what we could do is, well, we know a is equal to integral from a to b of f of x dx. This is the same thing as writing, well, integral from a to b of y dx. So again, f of x is just y, so we could write it like that. So what we'll instead do is substitute, substitute y equals to g of t, and also x equals to f of t. And then the idea is to remove these x variables. And basically replace them with their parametric counterparts, the t. So we could do that. Well, we replace y equals g of t, and now we have x here. When we take the derivative here, or the differential, we get dx equals to f of t dt, like I've done before in the substitution rule. So now that we have this, this is the derivative like that, f of t, f prime of t dt. So now we can replace dx with this, and then the next one here, the a and b, again we're going to assume at x equals to a we have t is equal to alpha, and at x equals to b we have t is equal to beta, like that. So when we replace all of these together, what we end up having is a is equal to the integral from alpha to beta of y is g of t, and now dx is f prime of t dt, like that. And there is our formula for the area underneath a parametric curve. So that's the curve, but also sometimes what happens is if this is increasing from alpha to beta, sometimes the other way around might actually be more aligned here. So sometimes you might have the beta actually being the leftmost point. So if, or basically I'll just write, or if the leftmost point, point is basically f of beta. Again, that's the x coordinate, and then g of beta for the y coordinate. If this is the leftmost point, then basically we could just write this as the same thing, but we just move these around. So a is equal to beta to alpha of g of t, f prime of t. And this will make more sense as I get through some examples in later videos, so stay tuned for that. And basically this is just showing that because the parameters don't necessarily mean like indicating which point is on the curve based on the value of the t. Sometimes t, if it's negative, for example, could be all the way to the right. Sometimes if it's positive, it could be all the way to the left, etc. Just to show you, just so you don't get a negative area if you're trying to calculate it, etc. If you're looking for an area. Anyways, that's all for today. If you learned, this is just a quick introduction to areas with parametric curves and how to use the substitution rule to write the integral into it in parametric form. And yeah, in later videos I'll go over some pretty cool examples, so stay tuned for that, and thanks for watching. And yeah, stay tuned for another math easy solution.